In a lab, researchers took a kidney that was the wrong blood type for every patient waiting to receive it, bathed it in a solution for 2 hours, and turned it into something that should have been impossible: a universal organ compatible with anyone. Before going further, it's worth being precise about what this story actually is, because the title framing deserves a quick correction. This isn't primarily a story about artificial intelligence cracking a medical mystery. It's a story about enzyme biochemistry, decades of careful immunology research, and a genuinely elegant discovery about the molecular structure of blood itself. AI and machine learning do play a real supporting role in modern versions of this research, particularly in helping scientists screen and predict which enzyme candidates are worth testing in the lab, a real and increasingly important tool in this kind of work. The core breakthrough here belongs to biochemists, immunologists, and transplant surgeons, not to a chatbot. That distinction matters, because the real science is genuinely remarkable enough to carry this story on its own. Let's start with why blood type compatibility exists in the first place, because understanding the actual biology makes everything that follows make sense. In the early 1900s, an Austrian immunologist named Karl Landsteiner made a discovery that transformed medicine. He identified that red blood cells carry specific molecular markers on their surface, called antigens, essentially tags the immune system uses to determine whether something belongs in the body or represents a foreign threat requiring attack. Landsteiner identified the A antigen, the B antigen, and blood carrying neither, which became known as type O. Before this discovery, blood transfusions were genuinely a dangerous gamble. Doctors transferred blood from one person to another with no reliable way to predict whether the patient would recover or suffer a fatal immune reaction. Landsteiner's work made transfusions predictable and safe for the first time in medical history, and it earned him the Nobel Prize in Physiology or Medicine in 1930. What makes type O blood special, and what still makes it special today, is that it carries neither the A nor the B antigen, making it essentially invisible to the immune system of a person with any blood type. This is why type O is called the universal donor. But that same property creates a genuinely strange, persistent problem in organ transplantation. Because type O organs are compatible with everyone, they're used up quickly, while type O patients can only safely receive type O organs in return. Type A, B, and AB organs will trigger their immune system. This creates a real, well-documented inequality in transplant waiting times. Type O patients often wait significantly longer for a compatible kidney than patients with other blood types, sometimes years longer, time spent on dialysis, a physically exhausting, life-limiting treatment that involves being connected to a machine for hours at a time, multiple times a week, simply to survive while waiting. In the United States alone, tens of thousands of people are currently waiting for kidney transplants, and government transplant registry data has consistently shown that several people on that waiting list die every single day before a compatible organ becomes available. This is the real human stakes underlying the research at the center of this story. For years, researchers have pursued various approaches to closing this gap, exploring the use of animal organs, developing artificial kidneys, and researching ways to suppress the immune system more aggressively so incompatible organs could be tolerated. Each of these approaches carries real, significant risks and limitations. But there's a different, more elegant angle that researchers began pursuing more seriously over the past decade or so, built directly on understanding the actual molecular structure of the antigens themselves. Here's the genuinely elegant biochemical insight behind this entire line of research. The A and B antigens aren't entirely separate molecular structures. They're both built on top of a simpler shared foundation, called the H antigen, which is what type O blood actually carries on its own, without any further modification. Type A blood has an additional sugar molecule, specifically a modified sugar called N-acetylgalactosamine, attached on top of that H antigen base. Type B blood has a different sugar attached in that same position. Type O blood simply has the unmodified base with nothing added. This shared structure is exactly what made the idea of blood type conversion scientifically plausible in the first place. If the difference between type A and type O blood really came down to a single additional sugar molecule sitting on top of a shared foundation, then in principle, you could use an enzyme, a biological molecule, specifically evolved to cut and rearrange other molecules with remarkable precision, to snip off that one extra sugar and reveal the universal type O structure hiding underneath it the entire time. In 2019, researchers, including biochemist Stephen Withers at the University of British Columbia, made real progress identifying enzymes capable of doing exactly this. Withers' team discovered that certain bacteria naturally produce enzymes capable of removing the A and B antigens from red blood cells. Laboratory testing showed these enzymes could convert type A blood to type O with remarkably high efficiency. This was a genuinely significant finding on its own, published in respected scientific literature and widely discussed within the transplant immunology research community. The next major step involved testing whether this same basic principle could work on entire organs, not just individual blood cells suspended in a lab dish, a considerably more complex engineering and biological challenge. In 2022, related research teams applied this enzyme treatment to donor lungs from type A donors, successfully converting the antigens present throughout the lung tissue itself. This process became known informally as ECO, short for enzyme converted O. The results suggested these treated lungs could potentially avoid triggering hyperacute rejection, the immediate, severe immune response that would normally occur when a fundamentally incompatible organ meets a recipient's blood. This was an important proof of concept, demonstrating the approach could plausibly extend beyond simple blood cells to complex, whole organ tissue. Researchers stopped short of actually transplanting these treated lungs into a living patient at that stage, given the understandably enormous caution required before testing something this novel in a real clinical setting. According to more recent reporting in late 2024 and into 2025, related research teams, including collaborators in China, took the next significant step, actually transplanting an enzyme-converted kidney into a human recipient for the first time. I want to be appropriately careful here, since I can't independently verify every specific detail of this particular experiment with full confidence, given how recent and specific the reported details are. According to these reports, researchers used a type A donor kidney that had already been deemed unsuitable for standard transplantation and would otherwise have been discarded, treating it for roughly 2 hours in a specialized perfusion machine, a device that circulates fluid through an organ to keep it viable outside the body, using it to deliver the antigen-removing enzymes directly into the kidney's tissue. The kidney was then reportedly transplanted into a brain-dead research participant in China with family consent, specifically as a research procedure designed to generate real-world data on how a converted organ would actually behave once connected to a genuinely incompatible recipient's blood supply. According to these reports, the treated kidney functioned successfully for approximately 2 days after transplantation, filtering waste and producing urine normally, before the recipient's immune system began recognizing the organ as foreign again, as the treated cells gradually rebuilt their original antigen structures over time. Researchers reportedly viewed this outcome as genuinely valuable data rather than a failure, since it directly answered an important open question. Roughly, how long does an enzyme-converted organ remain effectively invisible to the immune system before natural cellular processes restore its original antigens? A 2-day window, if accurate, would represent a meaningful, usable head start, particularly once combined with the kind of immune-suppressing medications and antibody therapies already routinely used in standard transplant medicine. Tools that weren't used in this particular experiment, specifically because researchers wanted to observe the treated organ's natural, unmodified immune interaction first. If these findings hold up under further independently verified research and peer review, the implications for kidney transplant medicine would be genuinely significant. Rather than type O patients being limited exclusively to type O donor organs, enzyme conversion could, in principle, open up type A, type B, and even type AB organs as viable options, potentially closing a waiting time gap that's disadvantaged type O patients for decades. It's worth being clear that this technology, even if it continues to develop successfully, wouldn't eliminate the ongoing need for immune-suppressing medication after transplant. The enzyme treatment isn't a permanent fix, since converted cells naturally rebuild their original antigens over time. What it would offer instead is a meaningfully expanded pool of potentially compatible organs, combined with standard post-transplant immune management, rather than a complete replacement for existing transplant medicine. It's genuinely worth understanding the specific biochemistry involved here in a bit more depth, because it illustrates real, careful scientific reasoning rather than a lucky guess. The most prominent enzyme approach explored in this research uses a pair of enzymes derived from a particular species of gut bacteria, working together in sequence. One enzyme first removes an outer molecular layer, and a second enzyme then removes the core sugar molecule responsible for the A antigen specifically. Separate research efforts have identified different enzymes capable of performing a similar function for the B antigen, and some researchers are exploring genetic engineering approaches specifically designed to make these enzymes more stable, more efficient, or faster acting for future clinical use. This is also genuinely where artificial intelligence enters the research pipeline in a real, meaningful, but appropriately limited way. Rather than researchers testing potential enzyme candidates purely through slow, exhaustive laboratory trial and error, machine learning models can help predict which enzyme variants are more likely to have useful properties, like improved stability or efficiency, before committing significant laboratory time and resources to physically testing them. This kind of computational screening has become an increasingly standard, valuable part of modern biochemistry research generally, and it plausibly played some supporting role in narrowing down candidate enzymes for this specific line of research. That's a real, legitimate contribution. It's a meaningfully different claim, though, than suggesting an AI system independently solved blood type incompatibility, which overstates what actually happened and sidelines the genuinely difficult biochemical, surgical, and clinical research that made this breakthrough possible. There's a real practical reason this technology's first major application specifically targets kidneys rather than every type of organ, and it comes down to basic biological logistics. Kidneys are comparatively hardy organs, capable of surviving outside the body for a meaningful window of time once removed from a donor, which makes room for a roughly 2-hour enzyme treatment process without excessively compromising the organ's viability. Hearts, by contrast, have a considerably shorter preservation window, often only a handful of hours total, meaning adding 2 full hours of additional treatment time could risk damaging the organ before it even reaches a recipient. Livers and lungs fall somewhere in between. Researchers are actively working to shorten the enzyme treatment process itself, and if that treatment time can eventually be reduced substantially, the approach could plausibly extend to a wider range of organ types beyond kidneys specifically. It's also worth acknowledging a genuinely important equity dimension to this research, one that goes beyond pure biochemistry. Well-documented disparities already exist in organ transplant access, including longer wait times and measurably worse outcomes for patients from some minority communities. Disparities with complex roots, including differences in blood type distribution across different populations. If enzyme conversion technology becomes a safe, reliable clinical tool, it could meaningfully reduce one specific source of that inequality. Though researchers and policymakers working on this technology have also been appropriately careful to note that ensuring genuinely equitable access to any expensive, complex new medical technology is a real, separate challenge, requiring deliberate policy attention, not something that happens automatically just because the underlying science works. The regulatory path from a promising experimental result to routine clinical availability is also worth understanding honestly, because it's typically slow by design, and for good reason. In the United States and Europe, any new medical treatment has to pass through formal multi-phase clinical trials before regulatory approval for standard use, a process specifically built to rigorously establish both safety and effectiveness before a treatment reaches ordinary patients. The kidney transplant experiment described in recent reporting was conducted as a specific, tightly controlled research procedure using a brain-dead research participant, not a step toward immediate routine clinical use. Turning this into a treatment available in ordinary hospitals will require substantial additional research, including trials in living patients using standard immune suppression protocols to establish genuinely reliable long-term outcomes. There's also meaningful related research exploring whether similar enzyme-based approaches could extend blood transfusion compatibility more broadly, converting stored type A blood to type O to help stabilize blood bank inventory during periods of high demand for universal donor blood. A genuinely practical application if it continues to develop successfully. Some researchers have also discussed, in more speculative and considerably earlier stage terms, whether comparable enzyme approaches might eventually help address other transplant compatibility barriers, including some of the challenges involved in animal-to-human organ transplantation, though this remains a much earlier and more uncertain area of research by comparison. What makes this story genuinely compelling, stripped of any exaggerated AI framing, is that it represents exactly the kind of patient, incremental scientific progress that rarely gets the dramatic headline treatment it deserves. It took Landsteiner's foundational discovery of blood type biology in the early 1900s, decades of subsequent immunology research mapping the precise molecular structure of blood antigens, the 2019 discovery of enzymes capable of actually removing those antigens, the 2022 proof of concept work extending that approach to whole donor lungs, and finally, according to more recent reporting, an actual human kidney transplant test, each step building carefully on the one before it, each step published, reviewed, and scrutinized by other scientists along the way. For the tens of thousands of people currently waiting for a kidney transplant, and specifically for type O patients who've historically faced the longest, hardest waits in the entire transplant system, this research represents something genuinely meaningful. Not a guaranteed cure delivered overnight by a piece of software, but real, careful, peer-reviewed progress towards solving one of the most persistent, quietly devastating inequalities in modern transplant medicine. Built the way real medical breakthroughs actually happen, through patient, collaborative, rigorously tested science. If getting the honest, carefully sourced version of medical breakthroughs, including a clear picture of what AI actually did and didn't contribute, is what you're here for, subscribe. Because the real story behind headlines like this one is almost always more interesting and more genuinely earned than the flashier version.